Kellen Donahue back here, who is our business development manager here in the West region. He joins me here today. We're going to walk through Heartland's technology, which was alluded to just a moment ago, into some further detail, and I think you'll find that this will kind of reinforce a lot of the comments that were made and give you a real-world example of some of the principles around, thermal conversion of organic feedstocks and how we manage it. There we go. So briefly on Heartland, we are a technologist based out of Murfreesboro, Tennessee. We have a suite of technologies which I'll talk about here very briefly in just a moment, more individually, but we have systems deployed around the country, both on our foundational technology, which is our concentrator, and a membrane technology as a companion. We also have the HelioStorm technology, which we'll be deploying in the industry probably in the coming year. And you'll hear more about that in more detail, but we specialize in a couple of things. On the liquid side, assured PFAS separation, and on the thermal conversion side, assured PFAS destruction. And our technology is geared toward a specific market vertical. We're not the mega system that you might think of when it comes to traditional gasification and pyrolysis. We're a scalable modular approach, and we have selected municipal biosolids as a preferred vertical to address some growing needs and concerns around that particular concern around contaminants of emerging concern. As I said, we have our foundational technology, which is the Heartland concentrator you see depicted here, typically for landfill leachate and other difficult to treat liquid streams, and 20 projects around the country, operating in 10 different states. And in a separate conversation, I'd be glad to walk you through that technology. It's quite compelling and tried, true, and proven in delivering great results today. And there they are. You see their reverse osmosis system, which can work in conjunction with the concentrator. But today we're going to focus on the LTC dry and the HelioStorm technology for thermal preparation and thermal conversion, as I said, within that biosolids arena. Why do it? Because regulations are changing very rapidly, very dynamically. There is a range of different approaches on a state-by-state basis, so a lot of the emphasis is really on what is the EPA going to do or not, but really, truly, the real trick here is to understand on a state-by-state basis what is happening regulatorily and what the legislative actions are going to lead to, and that's resulting in a lot of angst and anxiety on part of municipal utilities around the country. We believe we have a very compelling solution. I want to credit, this is courtesy of Hazen, a very well-respected consulting engineer in the space. They developed this graphic, and we've borrowed it, and you'll see it if you spend any time around the water space and water industry. You'll see this used by others besides me, but it's a very telling example and illustration of what is going on regulatorily around the country and why we have selected biosolids as the market vertical we think where HelioStorm can be brought to bear for the best effect. So let's focus on the two pieces of the thermal conversion strategy and the service that we offer. The first is the LTC dry system. This is truly unique and novel, and unlike probably any other dryer that I've certainly ever seen. I've been doing this for over 35 years, and I've never seen a technology like this before. It's genius in its simplicity. We're going to go into significant detail here in just a minute with a video that will even show you how the system operates, but it offers tremendous advantages around safety, low energy utilization, the range of materials that it can accept on behalf of a utility, the forgiveness that it can offer with regard to the preceding processes that lead up to it, is truly, truly unique, and we're very excited about it. There's a tremendous amount of enthusiasm about this technology as we have been bringing it to market in the last couple of years. it works hand in glove and in companion with the HelioStorm technology, which was previewed just a moment ago in a slide, and we're going to break that down in pretty good detail as well. Yes, it operates 3 to 10,000 degrees Celsius in its normal operating range. We do that through plasma technology. It's extraordinarily high, crazy, stupid, hot environment that is nearly impossible to measure with any real accuracy, quite honestly. But it's pretty exciting, and let's proceed on here. How do we typically configure this? Well, here's an example of what we would encounter in a typical municipal POTW scenario, right? We encounter begins with a dewatered biosolids stream. In this case, I also want to offer some indication of how the volumes and the tonnages are affected through this. But we'll begin with the dewatered sludge. We can offer dewatering as well as part of our technology train. Typically, we'll start with our base reference design of a 50-ton per day plant. That's 2 truckloads. For those of you who may not be familiar with municipal biosolids, think of 2 18-wheelers full of dewatered biosolids at about 20% solids. If you take that 50 tons at 20% solids, we take that, we deliver it to the LTC dry. That's low temperature conductive drying, and that's the explanation behind the letter. Take that, and we'll convert that to 11 tons of material at 95% dry solids. This is very much like what you've seen if any of you have seen the pelletized or dried biosolids material. It looks very much like that. We then take that and we'll feed it into the HelioStorm platform, and we convert that to 2 tons of PFAS-free innocuous char, free of PFAS, free of carbon, free of any other constituents. And it was alluded to earlier, it is the result of the organic stream being put through the high temperature environment and then quenching down to its lowest state of energy, which is the char, which is eligible for a range of disposal options. We typically take responsibility for the entirety of the technology and the deployment of the project, and I would tell you that we don't typically envision using this for agricultural purposes. This has other utility and disposal opportunities with cement, concrete, construction aggregates of all sorts, but it's also eligible for simple landfill disposal as well. It doesn't really offer any agricultural benefit because it's, again, free of the carbon, it's free of a lot of the nutrients and other things that might make something like that attractive to agriculture. This does not. So it really is innocuous and eligible for easy management in conventional ways. Now, the interesting thing here is that we take that syngas, which was mentioned, that is syngas, for those of you who may not be familiar with it, is a combination of carbon monoxide and hydrogen with some trace elements left behind. In our case, it would be a little bit of nitrogen given the carrier gas that we use. But we'll take that syngas, and it's a very high energy value stream that we can repurpose and bring down into a integrated genset in the project. That genset is capable of making enough power to support the operation of the HelioStorm technology. And we can also take the waste heat and bring it back and support the dryer. So the dryer is designed to work on a waste heat stream as its source of energy. Now, we don't make enough energy to put back on the grid. We probably don't make enough energy to support the entire balance of plant items that you would typically find, the oxygen, nitrogen generators, and the like. We do make about 70 to up to 100% of the energy we would need, depending on the organic content of the feedstock coming in. So that's usually a question I unfailingly get, and in this case, I would just want to point out you can take away from this that we make about 70% of the energy that we would need for a typical project. Okay, so let's talk about the Heartland Dry, LTC Dry. Really interesting system. I'm going to segue right into a video that I can narrate over here, but these are the key components. You're going to see a silo, which is a reservoir of the hot material where we can control the preheating of and pre-preparation and conditioning of the material. You'll see a incline auger that transfers that material with the new material injected in, and it will travel upward. We pull off the dried material that we need and back into the silo. Once again, as I said, I've got a video coming up, I think, in the next slide that will demonstrate that. But this is a truly unique design in that there is no dryer air. So we're not blowing air. We're not doing convection heating here. What we have is a conductive heating environment where you have a particle imparting heat to the next particle, and that's how the heat is exchanged. So there's no drier air, meaning that there's no a limited amount of dusting, which leads to explosive conditions in dryers. And as I was at WEF earlier this year, the statement was made in the workshop that, you know, if you own a dryer, it's not if, it's when you will have some sort of explosive event in a dryer. Because we don't have the air blowing around, we operate in a severe vacuum environment. We have very minimal dusting, therefore we have a much safer design here that will avoid that potential. We operate, again, under severe vacuum, so we're able to evaporate water at 150 degrees. It minimizes the potential for volatilization of PFAS compounds into the environment. Again, owing to that high vacuum condition, we have no fugitive emissions. Everything is retained within the dryer operating environment, so that limits odors, any fugitive emissions, including PFAS. We don't operate at high enough heat to really volatilize the PFAS in the first place, so it offers a lot of advantages. All that under the umbrella of the fact that you have in typical drying, you would need about 1,800 BTUs per pound of water evaporated. We operate around 1,000, so we're 35–40% lower energy demand with our design. So here's that video I promised you. We begin with the material in a heated reservoir or silo, if you will, with an inline heat exchanger. We're operating off that waste heat. We drop down into an inclined auger. All of your evaporation is occurring in this area right here, right? And we're injecting the wetter material into that vacuum environment, so it's not difficult to introduce the material. It is drawn in by virtue of the vacuum. As I said, all of the evaporation occurs in the first lower auger. We'll pull off the vapors of evaporation, condense them, and that returns back usually to the head of the host facility. We'll bring the material on up. We'll draw off the dried material through a vapor vacuum lock system, and that goes to HelioStorm. And we'll return the material back into the silo for a cycle that just goes over and over and over again. And there's very few exotic parts. Nothing here is made of unobtainium. There's no difficult materials to source. It's very conventional, simple, mechanical disciplines involved in the design and the operation of the system, and easy to maintain and operate. This is just a slide that illustrates that efficiency curve. As you can see, we operate, you know, at a range of 150 degrees or so. We operate at a much lower sensible heat required for the processing of the material, and the overall energy demand is pretty minimal compared to conventional designs. So HelioStorm, which is kind of the star of the show. Here it is. As I said, it is very versatile. It can process a range of materials. And now, even though we are focusing on biosolids as a preferred market vertical, and there are good reasons for that. That feedstock is plentiful throughout the country, if not the world. It's generally uniform in its nature. You know, there's a recognized anxiety and certainly a high level of enthusiasm around better management of biosolids and what can be possible with regard to how we manage the waste, how we take material out of the environment. Not to suggest I spent a lot of my career in managing biosolids for beneficial reuse in an agricultural environment, but I'll tell you that there are better ways to do it. We believe this certainly fills that need, and this can accommodate a range of POTWs that might not otherwise be eligible for gasification thermal conversion technology. But not only can it do biosolids, you'll see that it can handle plastics. It's a great solution for end-of-life plastics and other materials that we can get, we're approached weekly about different ideas of things we hadn't contemplated, actually. So anyway, moving on here. We can offer assured PFAS destruction. We use multiple plasma arcs, which you'll see demonstrated in a moment. It is electrically driven. Scalable, we can scale upward almost infinitely. So it's just a question of how much material is required. You couple enough of the HelioStorm systems together to accommodate that need. There's literally no upward limit of how much material we can accommodate. But we do have a base reference design, and we do try to avoid bespoke engineering. And we have a train next to a train next to a train is that scalable modular design that we talk about to accommodate that feedstock. Syngas. A lot of the syngas. Not all syngases are created equal. That's the way I'd say that. We don't require a thermal oxidizer on the back end of the process. So we don't have to clean up any tars or any other contaminants in our syngas. It's very clean inherently by virtue of the process. Therefore, we don't have a thermal oxidizer. We don't have a stack in the design of our project. So there's no Title V permit. There's no emissions other than the combustion gases from the generator that's integrated into the design. And I talked about the char just a second ago. Real quickly about plasma. You hear reference to plasma. We are certainly a plasma-based design. The question is, do any of us really have a readily available definition of what plasma is? We hear about it, but plasma is a fourth state of nature. It's a charged gas, essentially is what it is. It's the most plentiful form of material in the universe, largely because it's what stars are made out of. But we encounter it in our daily lives in a whole range of different sources. You can see it in lightning, the northern lights, which not all of us are privileged to witness, but that's what the northern lights are, the corona of the sun. Neon signs, plasma etching, plasma TVs are other examples of this, and as we encounter plasma, in our life. The interesting thing is that you can have thermal and non-thermal plasma. Thermal plasma can be harnessed to convert PFAS molecules into their non-toxic, non-threatening constituents, their ionic constituents. And that's what we do with HelioStorm. As you can see an example here, traditional gasification, pyrolysis, incineration that was mentioned before my presentation here, you're somewhere under 1,000 degrees Celsius. And you can certainly accomplish some destruction of PFAS at that level. I'll not deny that, but there's some question around how thorough that destruction really is at those temperatures. Long chains versus short chains, and things. There's a whole other line of discussion about that whole topic. The difference here, and the point that I'd like to make, is that we operate beginning at about 3,000 degrees centigrade, and we go up to about 10,000 degrees centigrade. We stop at 10 because we're not really sure what the upper limit really is. It's very difficult to measure temperature when you get that high. The surface of the sun is 5,000 degrees, so it's extraordinarily hot. That being said, it's also a very safe design. You could stand next to it if it were there where that projector is. I could stand here easily while the system is running. I could put my hand on it. It wouldn't be dangerous to do so. So you don't need 3 cinder block walls between you and the system while it's operating. So here's a video
Introducing
that describes it best.
HelioStorm, a novel ultra-high temperature plasma synthesis reactor specifically tailored for biosolid treatment applications. Unlike traditional technologies that require large-scale infrastructure, HelioStorm is small and modular, roughly the size of a refrigerator, scalable to projects of all sizes. The electrically driven HelioStorm consists of 3 zones: preconditioning, plasma ionization, and reforming. In startup, the preconditioning zone's plasma torches initiate. As voltage is applied across electrode pairs in each plasma module, a uniform plasma field rapidly cascades throughout the reactor, achieving temperatures up to 10,000 degrees Celsius. Dried feedstock is gravity fed to the preconditioning zone, where it is heated and volatilized. Then it continues to the reactor's ionization plasma zone. Here, ultra-high temperatures rapidly dissociate organic molecules into hydrogen, carbon, and oxygen species, breaking the carbon fluoride bond and destroying contaminants such as PFAS. Entering the reforming zone, ions rapidly cool into their lowest energy state, a clean hydrogen and carbon monoxide gas, or syngas, for conversion into renewable electricity. The remaining inorganics and minerals exit as an inert, PFAS-free char for use as an alternate low-carbon building material. Through its feedstock adaptability and small size, HelioStorm is uniquely positioned to tackle today's waste management challenges, destroying emerging contaminants and reducing waste by 95%. Contact Heartland to learn more.
So that does a better job of illustrating it in real time, helps you really visualize what HelioStorm is capable of doing and how it operates internally, and we find that very helpful in our description of the system as we try to explain it to audiences. I did want to touch on real quickly the emissions profile. This is, again, another question I'm always asked. We have done some modeling working with the genset manufacturer. We are well below and beneath any concern around a threshold of any reporting thresholds. Coming out, you see what we have here is the untreated emissions coming out, and then after treatment, what the final emission quantities would be expected to be. So we have no concerns about emissions. We've had no difficulty permitting the system in our home state of Tennessee. And we do not anticipate any other concerns in any other states as well. I've presented this to probably now a dozen state regulatory agencies, and there's been no concerns about emissions and any difficulty receiving permitting at all. We have a white paper. You're certainly welcome to grab the QR code here, and we'd be happy to share our white paper that describes everything that I'm talking about here today in more detail. And actually just co-authored another technical paper that's forthcoming, so we'll have another paper to share with the industry here very, very shortly in the coming weeks. But we took a pretty prescriptive approach to our analysis of PFAS destruction. We work with outside third-party entities, including Mastardi Plot, PACE, Montrose, for testing at our facility in Tennessee. And we're very proud of the results. They actually exceeded our expectations. We've tested the syngas, we've tested the char, we've tested the mass balance across the system. Each and every time we've done that, the PFAS destruction has been demonstrated conclusively, and it leads us to further and further development of the technology. And we're actually, I think I have the next slide illustrates that here. Yes, we used a Tennessee Biosolids, the source of which I can't reveal, but I would just ask you to think of country music, and that might lead you to conclude where the material came from. We're located in Murfreesboro, Tennessee, and it's pretty close source of dried material to us. But we have a very challenging feedstock that we baseline tested. They use a very high level of inorganic coagulant in their processing ahead of their own dryer. It's 40% ash, which makes it very brittle and hard to penetrate. Our system did very, very well, however, and we were able to achieve over 99.9% destruction of the PFAS in the feedstock. And there's a tremendous amount of detail that we can go into. The time here today will not allow, but as you can see, we are well on our way to demonstrating the level of destruction that I think that will put us in a market-ready condition for the technology. I often get asked about the balance of plant. If you'd like to catch up with me after the discussion, happy to share with you the individual components of this, but it's a pretty conventional design based on the backbone of the LTC dry feeding the HelioStorm dryer, and I can demonstrate to you, where the syngas goes and how it's being used, where the waste heat is going, where the water flows are, and how we can design a system that will accommodate not only dried or dewatered material, but also liquid as well. Finally, this is our technology center in Tennessee, where we have constructed a demonstration facility, and you can see an example of HelioStorm that we have now in operation, and this is what we use both for client trials, and we can bring the client materials in, and we can quantify the performance of HelioStorm on a client-specific feedstock. We have other units that allow us to do the R&D work that we like to do on plastics and other feedstocks as well. Here you see the dryer that I started the conversation about, and this is the LTC dry system that we have in operation in Tennessee as well. We can, like the HelioStorm, we can conduct trials and evaluations on client material, all that to facilitate a risk-free decision-making environment where you can bring, if you're a utility, you generate feedstock, you can bring it to our facility. We can operate it there and quantify materials reduction, PFAS destruction, and all of the other characteristics that you'd like to have quantified. We're quite capable of doing that. So if you leave here with no other recollection of this, just know that you have an open invitation to join us there in Tennessee. We'd be delighted to have you come see the system and walk through it and have a demonstration of your own. Finally, this is a slide just to suggest that we're happy to work with the client in a range of commercial models, whether you'd like to acquire it as a CapEx ownership or you'd like us to operate it for you and for a long-term service agreement after the fact. We're happy to do that. But this also illustrates an example of the project that you could expect. And if you notice, as I mentioned earlier in this conversation, it's a tight, compact design. It's about 100 by 100 square feet, and notice there's no stack here. So there's no alleviates a lot of the permitting concerns that you might encounter with a thermal conversion facility. This is not incineration. It's not combustion. There's no permits aligned with that kind of an approach to this. And there. Thank you very much for your time. We're grateful for the opportunity to speak with you this morning, and happy to answer any questions later. With this, I'll turn to Tim.
Thank you, Jim. Look forward to visiting you in Tennessee. Okay. Our next presentation is Scale-Up Demonstration of Waste Conversion Technologies. A.B. Goodman is Research Engineer at Southwest Research Institute.